Hello everybody, and welcome to another episode of Reasonable Coding, a live stream of reasonable software engineering, if you want to call it that. It really is just me trying to learn some stuff in public. Hopefully you get to learn some of it as well. Hopefully some of the things I say make sense, and if anything that I do say or do live doesn't make sense to you, feel free to ask, or if you know better, then just, call me out on my bullshit and we'll fix it on the way. Today, I would like to talk about algebraic effects, what they are and how we can use them. But rather than just me babbling about, them, I figured it would be a nice thing for you to see me fuck up over and over again by learning the F language. I haven't actually taken a look at F before. This will be the first time that I install it and run it. Of course, I've read what it is. Otherwise, I wouldn't be using it here, right? So yeah, today I'm going to install F. And we're going to be going through the documentation, trying to understand what algebraic effects really are from a very pragmatic standpoint, trying to make sense of how we would use them, and whether we actually like them or not, or at least whether I like them or not. I do not know yet. It might be that by the end of the stream I am completely in love with them and I just want to go and re-implement the same pattern in every other language. Or it might be that I think they're cool, but whatever. There's a lot of cool things that go nowhere. So we'll see how that goes. No. Sorry. I'm opening Twitch on my phone so I can keep track of the chat. And I accidentally started watching the live stream. Okay. I'm out. Alright, so let's begin from the beginning. What the hell is F? Oh, yes, before I forget, all of these videos will end up in Twitch. So you can see here, you go to videos, you will see them there. But since Twitch has a policy where they will remove videos after around 14 days or so, I've started collecting them in YouTube. So you can go into YouTube and type reasonable coding and you'll find out the videos that I've done in the past. There's quite a few hours of content last time I checked. There's at least a few days of full-time streaming of content here. Yeah, well, maybe not a few days. Maybe, okay, the 14-hour live stream is not here. So yeah, definitely not a few days. But you have some of them are most of them are around the Reason language and the OCaml ecosystem as well, which are very, very close, very similar, and are either building some utility libraries or inspecting some programs or trying to do profiling or learning how to do testing and whatnot. There's one in particular that's really interesting. It's about building design systems with ReasonML, where I invite a friend from Klarna, which is a payments company here in Sweden. It's a huge company. And he does design systems there. And it was very interesting to see that you can encode a lot of the properties of this design system into the type system of the language. And if you'd rather, you can also go into the playlist. There's one for ReasonML and OCaml, and then there's another one for Erlang that very slowly is going to be populated, where you will find some of this material available for later, in case you don't have the time right now to follow the live stream entirely, or while it is live. Okay, so let's go back into F. Now I'll just move these things around a little bit. F is a functional programming language based on algebraic effect handlers. This means that F provides handlers of not only exceptions, but of any computational effect, allowing you to redirect output, wrap state modifications in transactions, schedule asynchronous threads, and much, much more. Alright, we can try it on the browser, or we can install in our computer. I reckon we better try it out in the browser first, just get an idea of what it feels like, and then we can try installing it and playing around with it a little bit more seriously. Okay, let's finish out reading this thing. Algebraic effects on which F is built give rise to a uniform representation of all computational effects. Effects are thus first-class citizens of F, which makes sense, and can be seamlessly combined. There is no need for do notation, no need for monad transformers, and no need to reshuffle your whole program just to read a global flag. Interesting. Just like exceptions are a particular instance of an effect, exception handlers are a particular instance of effect handlers. Okay, I sort of start to see the parallel. Like in a language that has exceptions, you sort of have this parallel application that may or may not run, right? And only starts running the moment that you throw an exception from some call site, some function, and then the try catch that you have somewhere above it, right, in the stack, will actually be the program that begins running the moment you do a throw. And then from there you just keep going up, or you continue down the original program. So this might be, it is already saying that effect handlers are a more general thing. Okay, in F you can silence standard output, redirect it to a different channel, or even rearrange it. Interesting, sounds evil. Similarly, state modifications can be prevented or grouped into transactions. As handlers completely override the behavior of effects, there is no need for a default behavior to start with. F allows you to define your own effects. Just declare a choice operation and start writing your non-deterministic programs. Later, you can write a handler that computes a single possible result, an optimal result, or a list of all results. Huh. Okay, I get a gist of what this may be. So if we define an effect that essentially, may be called choice. I guess choice is the name they're suggesting here. Or chooses one among the series of things randomly or non-deterministically, to be more precise. And then the handler that will use this effect, just like in the exception we threw it, and then there was a handler for an exception that actually took care of doing something with it. Then the handler of this choice operation, which is an effect, will be in charge of saying, oh, okay, I'm just going to get the first result, or I'm going to get the best result out of all of them, or I'm going to get a list of all of the results that are randomly generated by this choice effect. But that is just my intuition, all right? So don't take my word for law. We will actually get into whether I'm right or wrong the moment we start actually using this. Okay, this is also test new concepts in programming languages. We discourage the use of F in production, and that makes perfect sense. It's prone to change. Good. All right, so try it out. I guess this link is the same one as this one. I'm going to go with the one below. And now we have a small program, and this looks a lot like a camel. It's a pity there is no syntax highlighting to make that even more obvious. But clearly we have variables, functions. If you're coming from Reason and haven't seen this before, this will be double X. It's not too different. Essentially, parameters go between the name of the function and the equals instead of having the little arrow. You can have recursive functions, mutually recursive functions. You can declare your own types, which is the same syntax as OCaml. And if you've never seen this in Reason, this is off. Essentially, it's having parentheses around it. And the little star that you see on the one here on the right is comma. This is how you do it in Reason. Potato, tomato, really, just same thing. As you can use pattern matching to define functions on such types. Okay, so area takes a shape, and based on the shape, it gives you the area. Cool, so the syntax is pretty much the same. This looks very familiar to OCaml. Okie doke. Let's go into the next example. Or we can try loading the file maybe. We have a REPL here. So if we do a shape, let's do the area. Area of, and let's create a circle with radius 1.0 float. Ta-da! Cool. 10, 12. Right, you get a gist. Cool. Let's go on to printing. The main premise of algebraic effects, which is what F is based on, is that each effect, manipulating memory, exceptions, whatever, arises from a set of basic operations. For example, a lookup and an update or raise. For example, we print out messages by performing the operation print. Interesting. So this print, right? Hello world, or hello. Oops. It's an operation, but I don't see it defined anywhere here. Maybe we need to, maybe it's defined somewhere else. Or unbound constructor. Print hello. Where does print come from? Let's load this file. So I guess that print is special to perform. I would expect this to be a value, right? That if I put in here, yeah, but okay, let's move on. I guess perform will make sure this exists somewhere. I am confused. Okay, where F really differs from OCaml is that you can handle such calls. For example, the program inside the handler will print A, B, C, and D, but the handler overrides it just as an exception handler will override an exception. Thus, the program should output just, I see you trying to print A, not so fast. Right, so the syntax here is not obvious, right? I guess if it was highlighted, it would be a little more clear, but you can say handle this expression, and then here you pattern match on the different effects that this expression is going to be working on, and based on that you will get the effect word here. I assume is for essentially knowing that you will deconstruct a particular algebraic effect value. And then you have key K here, which is normally the name that you give to a continuation. So in this case, it will be A first in message, and then it will try to perform a printing, but then it's not actually using K for anything else. So I presume that this is why, yeah, it doesn't print anything else. Oh yeah, you maybe wonder what the second parameter K is in a handling clause for print. It stands for the continuation, the part of the program that is waiting for the result to print. The difference between exception handlers and general effect handlers is that we may call this continuation, right? You may continue the application. For example, instead of stopping after the first print like above, we may handle it and then resume the continuation by passing it the unit type, or actually a unit value. The unit result expected from the caller print. Continuation should be called with continue K to be more easily distinguished from regular functions. Okay. So handle a bunch of side effects or algebraic effects, and then with, and we pattern match here on the different effects that we're trying to work on. This just prints a string, and then we continue with the next one, and this will actually print all of them. So I guess we could try some of these things, right? If we put this thing here, we say perform, and then we say print what? We get what printed out, and then if we want to handle this with a particular function, we just do handle. Oops, I might need to, yeah, perform, print, what? And then with, and then we can say effect, print, message, and then we don't call the continuation, so we can ignore it. Now, and here we can just say perform, print, and we can just concatenate the message twice. Oh, my bad. In this whole expression, this should be message. Cool. So now, interesting that we could, oops, sorry. This moves a little bit wonkily. Very, very sensitive to input. Damn it. Okay, there we go. We define the operation once, and then essentially the handler will actually be able to change what it does. Which may sound like a nice thing. I don't know in practice how well will this work. Imagine that you define a very complex program in terms of algebraic effects, and then somewhere down the line someone changes one of the handlers that you're using to do something different than you expected to do. So when I call this thing, right, I expect it to print what? But then for some reason, it's printing it twice. We'll see how it scales. Hopefully we'll see more complex examples as we go along the tutorial. I will call this a tutorial. And then maybe we'll get to try something locally where we can try to build a small program that uses them and see if we can shoot ourselves in the foot very easily, or maybe they're really robust. They offer really ways of abstracting this or dealing with this replacement of behavior. Okay. The handlers may be even more complex. For example, we may create a handler to collect all print calls, and instead of printing the string separately, the handler returns a combined string of all prints. Let collect, and we define a handler. Oh, okay, so instead of, we can do handle this thing with, or we can say with handler handle this thing. Okay. So we can define this handler beforehand and just say with this thing handle the other thing. I wonder if we can define it in reverse, right? Effect, and then we can print I'm just gonna do p perform p, right? With that handle, and then we said perform print a. No, it doesn't look like it. Anyways, so we have a handler here that's called collect. So when you get it's an X, it will just make a tuple. Okay, worth noting that this is not an actual computation. Sorry, it's not an actual effect. This is a regular value. We need to say effect in the same way that we would say exception when we're doing a match in OCaml or a switch in Reason, which is interesting. I wonder if when we try to run this locally and compile one of these examples, we'll get an error saying that we are not exhaustively matching all of the possible effects that we should try. But yeah, let's look into this handler. The handler essentially, if it matches an effect that's printing something, right, it will essentially call the continuation, and the continuation will call the next continuation and so on. So it will go through all of the handlers that it needs to go through, and then the last handler, right, will be called, and we'll return our result and a message. The continue, I reckon, goes back into the handler as well. I don't know, but if it did, then it would make sense because this matches the same tuple, right? Tuple type, where we have some x here, which will be the result, but then we have messages, which I'm assuming is the empty string, which is what we're trying to concatenate with the message that you had here. So this will essentially return to empty string, and this will be D, and then when it goes one level up, then this will be D, empty string, and then it will append C, and it will continue doing that, so we'll get an ABCD string out of it. Yeah, we can try that. Let's see if that makes sense. Run ABCD, and we have empty. Okay, so far this makes sense to me. Does it make sense to you? Any questions? I am confused about some things, like as I said before, how to scale these patterns a little higher, and why can't I just create a print value without using perform? Or what does continue do? Does it actually go back into the handler, or Okay, let's take a look at non-determinism. We will model non-determinism by implementing two operations, decide and fail. Decide, so here we actually build our own effects. Nice. Decide will be used to non-deterministically choose the correct path, while fail signals that a choice fails to return a suitable answer. Effects that do not need any input can be defined by using unit as input or with the alternative syntax demonstrated below. Where they are implicitly treated as effects with input of type unit. So effect fail is empty, and effect design will give you a bool. We use a trick to ensure that using fail type checks correctly by wrapping it in a function. For aesthetic purposes, we also wrap decide in a function. Ooh. Sorry about that. It's a little bit late. It's been a long day today. So we have a function called failed, and when you call it with a unit, it just does absurd. I don't know what absurd is. Let's take a look here. It's a function that if you give it empty, gives you any type. Okay, so I know what it means now. What is empty? It's a type, but what's the difference? Okay, it's not available. Is it a keyword? Okay, I have no way of knowing what empty actually is. And by actually is, I mean what it means in the context of this language. All right. So I'll assume that this can never run, and that this does run, and it will actually give us a boolean back. We create a few different handlers to handle the above effects. The simplest handler is choose true. That always decides to use true. Okay. A more interesting example is the choose max handler that returns the maximal result of all possible choices, while choose all instead returns a list of all possible results. Interesting. All right, so the handler takes an effect of decide k, and it just continues with the continuation giving it true. I think the max function should already be defined somewhere here. Yep. Okay. So it works for booleans. I wonder if it works for strings. And I guess it will work for numbers too. Yeah, okay, cool. In the case of choose max and choose all, the continuation is used twice. Right. Exactly. So choose max essentially branches off the computation so that whatever's going to happen after decide, if decide was true, right, actually goes all the way through and it gets executed or evaluated. And then you get something back. And whatever you get back will be compared against whatever you got back when you passed false. And then these two values will be compared to one another, and then you essentially pick the biggest one, or whatever max actually is here. I guess there will be a more general operation where you parameterize choose by a function, and then you branch off, true and false. Interesting. I guess you could express a very, very complex tree of computations that have to be compared to one another in an arbitrary fashion with this. And choose all does something very similar to what we did before, that if we get a decide, okay, it will just give you a true and a false and concatenate the results, which are a list of the elements. And if any of this actually fails, then you get an empty list. See, this is a thing that I'm not finding very intuitive just yet. I get that continue k true can fail, or false can fail, right? The continuation may fail. If you don't define what the failure is here, then who takes care of that? Like in this handler choose max, what happens if k true fails? I don't see any effect fail underscore some really low value. You know what I mean? So I don't know. I'm still learning out about it. But of course, choose all will go through all of the possible branches downwards from the continuation and then collect the results in a list. Okay. So here we just have different examples. I'm just gonna paste this in here. I'm just gonna load the file. It's gonna be easier. Then we can just run the expressions, right? If I do here choose true, then this will run, and we should see x being 10. So the result of this thing should be 10. Good. Now if we do the same thing here, I think the result should be 20. Because if decide is true, right, and decide is true, then you get 10 and 0. If you get true and false, then you get a 5. If you had false and true, you get 20. And false will be 15. So this should be 20. Cool. In case that wasn't completely obvious, what's happening here is that this body seems to be evaluated, right, twice. One for each decision being true and once for each decision being false. Which, because we're calling decision decide 2 times, it's actually, is it calling it 4 times? Is it computing this? I think it's computing the 4 different branches that we have here. So this with this, this with this, this with this, and this with this. And then it picks the highest result. So the maximum value of this expression. And choose all should give us essentially 10, 5, 15, and 20. 20 and 15. Okay. Close enough. We can use our Boolean decision to construct a decision over integers. In the decision, we only consider integers on an interval, m to n. Oi, oi, oi. Uh-huh. So we have a choose integer and m and n. And if m is bigger than n, then we will fail. But if it's not, right, then we decide true or false. If we get it true, then we return m. Otherwise, we increment m by 1 and we run the same thing again. So this will essentially go from, let's say we have a list of 1, 2, 3, sorry, what am I doing? 2, 3, 4. It will say, assuming the numbers are, the input to this function is 1 and 4, it will say, is 1 less than 4, bigger than 4? No. Okay, so give me a random boolean. If it's true, then I'll use 1. Otherwise, I'm going to jump into a list that begins with 2, so 2 and 4, and repeats the process. Is 2 bigger than 4? No. Okay, or, do I get a true or a false? I got a false. Okay, I guess I will call myself a recursive incrementing 2 by 1. And then we get to this point, and it says the same thing, and it will increment it by 1, and then we get 4. And it's going to be 4 to 4, and if 4 is bigger than 4, then it fails. So there is a chance this will fail. Interesting. But at any one of those steps that we just did manually, the decision could have been true, and then you just return a number. If it was a 3, you return a 3. If it was a 2, you return a 2, and so on. So it will go through all the numbers, and it will randomly, right, non-deterministically pick one. We can actually. Oh wait, I already have defined this. Choose int, and then we do like 2 and 3. So not catching effects is a runtime error. Interesting. I guess we would have to handle this thing, right? With, and then we can do effect decide. I guess we can do with choose all, handle that. And if I do choose max, then it should always be 10. Okay, so this is answering a question I had. What happened in the handlers that do not handle fail? So choose true will always return the first one. Choose all actually defines a handler for fail, so it will return an empty list when it fails, so it will get you a list of everything. But choose max does not handle this thing failing. I wonder if there's any value in statically checking that you're handling all of the effects that you may. Essentially, would the type signature of k here actually show that it may have failed with a particular failure, or how would that look like? Let's say even IDE support. In an IDE that supports this nicely. All right. So. So I see here some functions for essentially trying until you find something. Pythagorean theorem. We'll call int square root, which calls try, which is defined here. And try just recurses over, and as long as n2 is bigger than m, it will just return none. Otherwise, it will return some n. Otherwise, it will recurse. And this will choose the bigger integer, and then choose the smaller integer. Check if they're part of a path. Okay. And then this will try to find the square root of this expression. If it finds something, then it will return the 3. If it doesn't find, it will just fail. Which this will be very similar to throwing. We also construct an additional handler that simply tries to get one viable solution. The backtracker. And the backtracker actually has a handler inside of handler. Okay, so this is sort of how you would do that. So you have a decision, right? And you have a continuation. So the first thing you do is you go with a false, and if this fails, then you go with a true. If that fails, then you're screwed. Okay. All right, let's go through these examples then. When we run this, what do we expect to see? So Pythagorean for 5 and 15, right, we'll choose the integer that's the biggest between m and n minus 1. So a will be 14. And you will choose the smaller one from a and n. So between 14 and n, so that'll be 14 again. Wait, what am I doing wrong? Choose int, right? Oh, it yeah, right. It randomly picks one. So it will choose any number. Oh. Okay, so this will choose any number between 5 and 15, right? And this will choose any number between whatever was chosen here and n, which is 15. So this could be 5 and 15 again, or it could easily be 14 and 15, right? And here, sorry, it's between 5 and 14, so one less. You will always want, I guess that you don't want to have 15-15 situation, so you throw in a 14-15 worst case scenario. So then you have two different integers, and then you just try to square root them, and you add them, and then you try to find the square root. Sorry, you don't square root them, you calculate the power of 2. I don't know how to say this in English. You elevate them to the second power. Is that how you say it? That's how I would say in Spanish, at least. Anyways, and then you take the result and you try to get the square root, essentially by beginning with 0 and just trying a bunch of square roots. I tried a bunch of power 2's. Essentially increasing the number that you begin with on every round until you find something that is equal to the number that you're looking for. And if you find it, then that's your number, this n that you just found. If it's bigger than, then you know that you went overboard. Ahead. You're too big. The number is greater than what you're looking for, so you overshoot. That might be a better term. You overshot. Okay. And if you find something, then you return that. Otherwise, you perform an algebraic effect and you fail. And the backtracker essentially is built so that whatever you're choosing will try false, and if false fails, then it goes with true. Okay. So if we run this thing here, we will get a number back, right? And this number would have gone through the process of choosing different pairs of numbers between these two, and finding one that actually gives you that's actually the square root of the sum of both of the numbers to the power of 2. Okay. And when we do a choose all, then we will naturally get a lot of triples that are results. And we get 1. If we change this to 7, okay, maybe 9. There you go. And if we get this one, that's actually 4 different pairs. All right. Now we have the 8 queens problems. And here, 8 queens problems. Using the non-determinism approach, we can also solve more complex problems. For instance, the well-known 8 queens problem. I am not familiar with this problem. I assume this is different. No attack. You get 2 set of coordinates. What is the 8 queens problem? Let's quickly look that up, so we have a reference of what should we be looking at. Placing 8 chess queens on an 8x8 chessboard so that no 2 queens threaten each other. Okay. So we have a choose. That if you give it an empty list, it fails, but if you give it a good list, then it will decide whether to pick this one or choose from the rest. That's a function that returns an algebraic effect, or rather performs an algebraic effect, or returns a value. But if I go here and I type choose, yeah, see, this is, I don't know if this is actually doing anything more than what it says. That's so confusing. I was expecting the algebraic effects to actually be tractable in the signatures of the functions that use them. Because if they aren't, then how do I know what I need to handle? Or when? Okay, so no attack gives you, given 2 points, will tell you if you, okay, so if the x's are different and the y's are different and the absolute difference between the x's is different from the absolute difference between the y's, then you have a no attack place. Cool. For a given x, check available y. So this will just filter the list of 8 squares. For all. I wonder if this is new syntax or if this is a function as well. Okay, it's a function. So if you give it a, I guess this is a place. Or just a column, and you give it the queens, it will check that none of the queens, and these are the positions of the queens, okay, that none of the queens, actually that all of the queens have a no attack that none of the queens are actually in an attack position to any of the other queens, right? And then lastly we have, I mean, this essentially will give you true or false by checking that none of the queens have an attack position there, and if any of them do, then that that y coordinate will be filtered out of this list. So by calling available with the current queens and the position you want to place a new queen in, you'll be able to say, oh, I can place it in one of this or many of this, and so on. And lastly, we have place. And if you give it, of course, a y position, x position, and a list of queens, then it will check if it's 9, then returns the positions. Okay, it's going to be incrementing it. All right. And otherwise, it will just choose one of the available positions based on the queens that are already placed and the position you want to place it on. And when it chooses that, it will just append the tuple into the queens and recurse. Cool, okay. So that makes sense to me now. If we say place 1 and 0, then of course this will start by picking the first available position in here, which should be 1, I believe. And it will backtrack, so it will actually go back if it fails and try a different alternative. So if it happens that when we call choose here, right, with an empty list that will come from filtering everything from here, then the backtracking handler for this particular algebraic effectful operation will try again the whole thing, but instead of using decide as true, it will use false, or instead of using false, it would use true. So let's run this and see what happens. I expect the first one to actually be 1, 1, and then I haven't seen the solution to the problem, but I reckon that if you are in 1, 1, then no one else can be in that column or in that what do you call this? Row, right? But you can't also be diagonally. So it might be that you need to be on the y-axis. You have to be at least 1 unit below, right? So if you had 1, 1 before, then the next one has to be. It can be 2, 2. Otherwise, you'll be on the diagonal, and that means the other queen can attack you. But you could be on the x2, right? On the y3, for example. That means you're not on the same row as the first one, and you're not on the same diagonal as the other one, as the first one. So I would expect it to be 1, 1, and then 2, 3, and then the next one actually could be 3, 3, 2. No, actually that can't be 3, 2 either. It will have to be 3, 5. Okay. So 1, 1, 2, 3, 3, 5, and so on. And I was terribly mistaken. None of those actually make sense. Or at least didn't make sense in these results, assuming the algorithm is correct. So we have 1, 8, and of course this begins from the back, doesn't it? So what happens if I just do reverse? That actually didn't affect anything. Might be that I need to rebind these things too. One, 1, and then it's 2, 5, and then 3, 8. Interesting. Okay. That aside, this is gonna go from 1, 1, and then on the next iteration it's gonna take a 2, and it's gonna ask, okay, which one of these these numbers here, these Y positions, are actually available because I don't have any, you know what? Because I have no attack zones there. No, as in there is a lack of attack zones. So essentially, I have a free. I'm completely free from all the queens to attack me. Interesting. I don't want to keep going into this problem. I want to go into other uses of algebraic effects. But it's very interesting to see that we can express essentially the exploration of these different branches of the computation very succinctly, just by saying, look, there will be a choice, right? It could be true or false. If it's true, you go somewhere. If it's false, you go somewhere else. And then you just say, please backtrack this for me. So if it goes into false, then you go, oh, okay, I need to actually take a look at the other branch instead. Probability, and I am not very good with probability, so this might actually, let's give it a shot. As seen in non-determinism examples, effects can be used to simulate choice. In order to use randomness, we also need to use effects. For instance, random int and random float. We can also use handlers to compute some properties, for instance, the expected value of a discrete random variable. Okay. We define an operation toss to use as random coin toss. Using the operation toss, we can define other distributions as well. Uniform. If we have just one element left, we return that. Otherwise, if we compute the next element from the length of... Okay. Why wouldn't it just be the length of the whole thing? It is. And then we divide 1 by the length. And that will be the probability of each one of them happening. So we do a toss. And the toss is a boolean. So if the toss is true, then we call x. Else we recurse on the... Right, okay. Alright, I get it. We're essentially trying to uniformly pick one of them. So essentially, the distribution here will be all of the possible values in this list have the exact same probability of occurring. So we'll just pick one of them. Random value. It takes random float. Okay. If it's less than p for some p that's specified in the float, then it just continues with the toss. And if this gets value, then it just returns value. Interesting. 1 second. Expectation. I still find this a little confusing to read. I expect continue to essentially go back into the same handler so that if you do get a value, then it just gets returned. But I would expect other effects that are not handled within this handler to essentially fail as be uncut. But then that means I need to look at how the parent code is actually going to handle, or if it handles some of these effects, to be able to determine how a piece of code that runs through this effect will behave. With expectation, handle let x uniform and y uniform. So if we run this, there's an equal chance of getting any combination of any of these additions of floats. Oops, I probably want to load the file. 7. Huh. I guess if I change the handler to be random value, then I will get something else. But I don't know why I was expecting it to actually give me random values. Oh, this is the expectation. Okay, never mind. So this is computing a value out of picking each one of the values from the continuation. Computing each one of the values from the continuation, and once it's done doing the computing of those values, adding the probability. Okay, so I reckon that this is a probability equation that I'm not seeing through the code. Random value should actually give us different values, and it does. It mostly gives us 7. Okay. We can also compute the distribution of outcomes for probabilistic computation. We first write a function that combines two outcome distributions, where the first outcome distribution is chosen with the probability p, and the second with probability p minus 1. Sorry, 1 minus p. Okay, I'll let that sink in for a second. We can combine probability distributions, outcome distributions. I unfortunately do need to take a refresher course in probability to unmangle this. Like, I can read through the function, but then what do some of these operations that we're doing actually mean? I do not know. We're going to be adding to yeah. If I try to, I will probably lie to you, and I'd rather not do that. So maybe we can get an intuition of what the distribution handler should be doing compared to the random value, for example. Okay. So this is the probability that each one of these outcomes will appear, I guess. I wonder if this actually adds up to 1. I am not going to manually verify now. I'd much rather go into the state examples, which might be closer to something we deal with every day. Or, I'm going to be more specific, something that I have had to deal with every day. I definitely want to get more into probability, but until I have an actual problem, I guess, at work or on a daily basis that requires me, I might not be able to put the effort, which is sad. I would love to know a lot more things than I know now, but one day at a time, one topic at a time. Today, it's algebraic effects. State. It is often beneficial to have some form of mutable state, which can be implemented using handlers. Below is an example of a simple integer state. Get and set. So off the go, I would like to know whether this thing over here could be parameterizable. 1 second. Right. Otherwise, this get and set will be quite quite specific. I guess that would be if we could functorize definition of effects, then maybe we have a state mod functor that you parameterize with whatever type you wanna use, and then it just defines new get on set effect for you for that type. So that could work, but continuing. The monad state handler wraps the computation in a function, and the state is passed around as the function input. The initial value of the state is given to the transformed computation as input. Okay, so the monad state, essentially, if you call get, it returns you a function that if you give it a state, right, it will call the continuation k to get the value, and it will call that with the state. Because k, or at least the continuation of k, applied to the current state, right, it seems to return a function itself. And we can take a look at that and say, yeah, it does, because the continuation should be this at some point. When we get some value out of get k, then we should get this function that I expect us to apply with the state, which is ignored, but I wonder if it has to be ignored. And then we get the value y back. And when we do a set, right, we have some value here s and the continuation, and then we just have a function, return a function that will ignore the state, but when you call it, it will call the continuation k with the unit value, with the unit, and whatever returns from there will be applied with the value of the set. Okay. So f with monad state handle, let x equals perform get in perform set perform get plus 10. And then it's calling f30. I'm gonna load the file. Let's have a look at this. No. Spoilers. So if I call f with 30, then we expect to see a get, so that x gets back, and then we set twice that, and then we add 10. So this should be 70, right? Oops. Didn't I just load this? Okay, reset, load, and then I can just do this. And it is 70. Okay, that makes sense. We can improve it by giving the state a default initial value using the finally keyword. The value of the initial value is given to the handler as a parameter. By modifying the case for values, we also return the result and the final state value instead of just the result. Right. So then we can thread this state around. The value of the initial state value is given to the handler as a parameter. Okay, so we call it, and then you get a handler that's parameterized. By modifying the case for values, we also return the result and the final state value instead of just the result. I'm confused. I am confused. So better state is initial, right? So then this will be executed at the beginning or at the end. So when I call this thing, we'll essentially perform get, and this will be sequenced, and you get a state, and this continue k, and k in this k, where does k come from? Is this thing actually this? Huh. So I wonder if these are the same thing. Or maybe like that. So the continuation here, right, will actually be this bit, the assignment that goes into this rest, right? So this is just a way of writing this. And then you call the continuation with the state. So it gets set up. Interesting. Right, I'm gonna remove this. We're gonna run the better state now and see what happens, see how it behaves. And then we'll try to dig a little bit more into it. Okay, so 70 is the last result, but this is the state that we actually set. The interesting bit is that we could essentially write that like print state, right? Handler, and here we could just do a bunch of side effects like perform, and then print, got a value. We probably want to do parents, and I think this will be a number, so string of int should be good for y, right? 2, 3. And then below that we can just return the fun as ys. Actually, I'm just gonna copy the rest. What am I doing? Just 3 spaces for indentation? I must be insane. Alright, so print, and then we say get, and then we can say, but we don't actually know what get is until we call this thing, I presume. So maybe what we need to do is put that inside here, right? So this will be next. Perform get, and then I wonder if next will be a no, so next has to be a function. Next has to be a function, so we invoke it, which means only after invoking this function will we actually get the value back. So if we do it like val or v, then we can say v here, and that's 1, 2, right? And then we just return the value. Like that. And we can do the same thing for set, or a similar thing at least, except the set will ignore the original state, but we can do next will be the function, the continuation, right? In let v, and this will be next s prime in, and then we can do perform set s or v actually. Would it? We'll have a look in a second. Alright, I think this should run. I do not know, but we'll have a look. So we don't have anything like string event. I'm quickly gonna save this code and look around and see if any of the other examples do anything like that. I don't see it anywhere. Nope. I guess we can do printing twice. We can print once and we can print again. So really, so we understand, oh, this is what we got here. Perform, print, right? Like that. Let's see if that works. Line 0, chart 27. Great. Okay, I'm not gonna do that. And that might be it. And then here we just have value. Okay. Try. Same thing. Print got a value, print. I am confused, and this is definitely not the best place to edit this. I guess I can do some terrible debugging. Okay, so that worked. And if I add a new class, that failed. Cool. So something around here failed. So if I remove that, you might get a better idea of where the error is. No! What? Oh, okay, so maybe getting the value is trying to coerce this into a string, and that's why. Yeah. Yikes. I don't have a lot of tools to figure out what the hell I could use to turn a number into a string. So for the time being, I'm just going to remove this print. I'm just going to let the print of the string be there. At least we'll be able to say, hey, get set and print got a value are being executed in this order or whatnot. Cool. So now we have that, and we can say with print state 20 handle this thing. And then we get the first thing that happens is that we got a value. Then we get something out of the state. Then we set something out of the state. And then we get it again. yeah. Yeah, I still need to mentally go from one model to the other. They're clearly a way of expressing continuations, like we saw before with the monadic sequencing operator. It's not entirely obvious to me, at least now, when each one of these handling cases will occur. And I have definitely no idea when the finally happens, because we could just add a print there, right? Perform, print, finally. Cool. So finally happens first, and that's how you get the value in f, which is the continuation. And then the next thing that happens is y, right? Got a value where you return a function that has y and then some state that you pass in. Now the third thing that happens is a get, and this returns a function. Yes. That will call the continuation. And then this goes one level deep again and goes into here. And so it returns a function, right? Next becomes this function. Whereas this function will do the same thing again. Wait. No, if that's what's happening, then the printing is confusing. Maybe. If I put the print above, just maybe. So that's the order in which the effects get handled, but that's not the order in which the continuations get followed or get evaluated. Okay, let's give this one more try. So the first thing that happens here, and I'm going to make this a little smaller so I can see everything. Get gets handled, right? And then this calls a continuation, K. But the continuation K how does it get to finally? Get gets handled. And it returns this thing, right? This function over here. Does finally always get evaluated? No, it doesn't always get evaluated. Maybe it only gets evaluated the first time you handle something, which I don't quite get. I was expecting to either see finally at the beginning or at the very end. Clearly, I am wrong about how this evaluates. So get handle gets called. This happens, and then we return a continuation. Sorry, return a function that is really a continuation. This continuation will actually call the continuation that we had. And I expect this k to be this finally, but I can't quite connect why. Well, it's interesting though that we're already experimenting with changing the behavior of a piece of code, or rather, what effects it's going to be computing, right? Without modifying the piece of code at all. We just change the handler that's going to deal with, the effects, and then the effects do something different. In this case, they also print something out. So we get handle, and then there's finally somewhere, and then we get a set handle here, right? And the set handled look at how everything unwinds much later on. So we're building up this computation. We're not evaluating it until we go to the very end. But then why doesn't it finally happen at the very, before we get to the very end? So maybe that's where got value happens. And then you just get this tuple back, and then you pass this tuple around across the continuations. But you're not destructuring for this tuple anywhere, so I don't see it being obvious either. So we're going to get, and then we're going to finally, and then we're going to set, and then we go again to get, and then at this point we actually get a value back. I wonder if that happens all the time. So for example, if I do let y perform get in, right? Then I think we were running with 20. What will we see? Will we actually see get finally get set get got get finally get set get? That's what I'm expecting. Okay, so that worked. Get finally get set get. And then at the very end, we do get the value. So I think that the value is only after we build up this computation, we will find ourselves here. And I guess that set, nowhere on here we're actually getting the value. So I'm gonna do something. I'm just gonna turn this into string state, right? Like that. So now this should essentially compute a state by getting and putting strings into it. We need to define these effects as well. So we're gonna reset this thing. Right, we got the effects there. I guess we can just load the file. Copying it just in case, load file. And we don't really need this monad state at all. No, we don't need the better state either. We just want this one. Look at that, nice. Fits in a single screen. There you go. Cool. So now we can actually add the values to this print, and this is just because of a limitation of the environment, I believe, right? Where I'll be able to say get handled and then get evaluated and say equals, and then just add the value that we got from the step. And I think in my head this makes sense, but I don't know if it will. So I'll just reset and load file. Oops. 1, 2, yes. 1, 2, yes. Oh. Parser error. Really? 1, 2, 1, 2, 3. Okay. Where did I go wrong? Line 3, 1, 2, 3. Type 27. String. What the hell? This is wrong. 1, 2, and 1 is a string, isn't it? Huh. Yeah, kind of hard to debug. I guess that I am doing a bad job at learning here. Oh. Yeah, okay. So I can't annotate values like that. What do you say if we move on to threads and see if things make a little more sense down there? Okay. So for threading, I'm gonna reset this environment and load things again. We have an effect for yielding, another for spawning. Then we have get next and add to queue. Okay. So this looks very similar already, where the get next effect will have continuation, and it will give you a function that will match on a queue, then you give it, and if it's empty, we'll continue with none. There's nothing to do, and there's nothing in the queue, and if there is something else, then it will just essentially give you some element, and that continuation will give you a continuation as well. Then you will call, and if it happens to be the continuation is a value, and this is that continue. I think I'm getting the gist of it. The continue will actually re-enter the handler with whatever value you end up having here. So if it's a value, then you'll just get this thing here. Then when you apply it with the tail, it will just return the tail. But otherwise, if it is another effect, then you will just get more stuff out of the queue or add more things to the queue. Okay, that makes a little more sense now than it did before. I'm kind of curious now. We'll get to the state after we go through threads. It might make more sense then. Let's round robin. Okay. So it will define an enqueue function that will add things to the queue, right? And a dequeue. That will essentially evaluate whatever we get out of the whatever next thing we have enqueued before. And there will be a recursive handler here. that for yield, right, we will enqueue k, so we'll put this in the queue and we will run whatever it's in the queue, whatever we need to run next. And for spawn, we will enqueue whatever we have as a continuation, and then we will try to handle t recursively by reinstantiating the handler that we have, and this will be our round robin handler. Okay. Because a round robin handler uses our queue, we must nest the handler. So you need to first give it a handler for the queues, and once that it knows how to handle queues, essentially you will tell it how to handle the different effects via the round robin effect handler. So you spawn two functions, and this brings Erlang memory back, which is nice. And the function that you spawn is an iteration over the different letters, right? Each one will try to print something and yield, which because of the round robin mechanism, anytime that you yield something, you will enqueue, but then you will dequeue whatever is next. So you will run something other than what you're trying to run. So executing this will build up this essentially series of prints that the round robin handler will throw at a queue and evaluate from the queue. I want to say by going A, B, B, C, C, D, D, E, E, but it might be very different. So I'm just going to run this and see what the outcome is. Okay, A, B, B, C, C, D, D, E. Alright, the intuition was correct. The handler in the queue, every time you yield, right, instead of actually evaluating the continuation or whatever happens after the yield appears, you will just put that in the queue and run whatever's on the top of the queue instead. And then we can run an unbounded amount of threads. The following example enumerates all the reduced positive fractions less than 1 by spawning a thread for each denominator between D and E. Okay. Fractions, and you have a recursive find fraction function. If the greatest common denominator for n and d is 1, then we have the string function. Oh, okay. We could have used that. When we were playing around with the state. That would have been nice. So we build up a series of prints and we yield after each one of them. I guess the key effect here is really yield, right? This is what we do to delegate a piece of work to the queue. Okay. Spawn a thread for next denominator. If D lesser than E, then perform spawn fun. So the first thing that it will do was just yield, and then afterwards it will just try to find the fractions for D plus 1 and E. Okay. So I'm not entirely sure what the behavior of this should be. Okay, so it finds a bunch of functions. I guess that you could potentially do non-determinism here by in your round robin, right? In Q or DQ, depending on how do you decide. So if I do if decide, then in Q, else Q, then I expect this thing to sometimes evaluate some things in one order, sometimes do it in a different order. And I guess I have to break some of these things from here, right? Yeah, no, that seems to be very deterministic to me, but of course, it could be that it's just I might be misinterpreting how to use them. Okay, interesting. At the beginning of this, I was kind of relieved because I'm okay with the syntax and the evaluation model of a camel. And then as we moved forward a little bit, I started to think that maybe effects were not as nice as people are trying to make them look like. Essentially, if I try to evaluate a piece of an expression that has algebraic effects in them, then it will be a runtime error whether I handled or didn't. So if I forgot to handle any particular effect, then I will get some sort of runtime error for them, which I didn't like. And then as I moved into non-determinism, what's it here? Yeah, I started to realize that some of these functions, even though they involve side effects, they're not reflected in the signature, which means, again, I have no way of knowing what they will actually be needing to get handled. So if your, for example, Pythagorean function actually needs you to tell it, hey, this is how you handle choosing, or this is how you handle failure, then I would expect it to be reflected somewhere and it to be obvious and mandatory to some degree. Might be a good idea to do some sort of like explicit upstream or explicit bubble up this particular effect full value so that an handler above handles it. But I do not know very well. The probability was a little confusing for me because I'm not familiar with the domain that well. The state one, turns out that you were really just doing continuation, CPS here, continuation, CSP. Continuation passing style. Yeah, CPS. Here, with a syntax that looks mostly imperative. Perform this and then perform that. I guess it's a better do notation for some definition of better. And then the thread one, this was actually quite interesting to see that with a queue that defines how to process each one of the elements in terms of these effects, then you can get some, let's say, concurrency. Now, I reckon that there might be some runtime support required to be able to execute some of these things actually concurrently or parallelly. It's not reflected here, so I can't really tell you, oh yeah, this is a great tool for that. I do know, however, that some of these ideas are being tried out in OCaml multicore to be able to enable multicore in a type-safe way, and that's about what I know of it. Let's go into learn more and see if okay. The best place to start is the white paper. And we're actually gonna be, not what I intended to do. We're gonna be reading this white paper if you wanna join. um, on Monday in one of the events that we have scheduled here. So I'm going to be starting a new series, like parallel to reasonable coding, that I'm calling The Literate Programmer. And the whole point is to sit down and read some things with people. So in this particular episode, which will be the first one, I'll be reading this paper by Mattia Pretnar. And we'll try to get an idea of how things actually happen under the hood. Like right now, we're looking at the language and we're saying, "Oh, this looks like OCaml," but then it doesn't really evaluate like OCaml, right? What's really happening here? And I know that the paper defines the denotational and operational semantics of the language, so we can have a look and more certainly or more accurately describe what really is going on. But you're all invited. Go in there, subscribe, if set a reminder like that, and then you won't forget. It's Monday 11th after work if you're in Europe. So after you've got dinner, then you can just sit down and read something with me. It might be terrible. I have no idea how it's gonna be. So wish me luck. And then there's more relevant literature. Okay. So there's a repo. I didn't know about this. Start. There's a library for programming in F#. There's extensible effects. Oleg Kiselyov. This guy has a bunch of really interesting papers on lightweight static capabilities, and I think lightweight higher kinded polymorphism as well. Fused effects, Idris effects. This is multicore camel. And then we have a bunch of tutorials. It'll be very nice to take a look at some of this. Let's see this. Papers. What's the first paper on algebraic effects? Oi. G Ford. There is certainly abundant literature on the subject, if you're into it. Let's try to get through the CUFB. Oh, I guess this tutorial is not online. Okay. Interesting. I know that Idris had an effect system in the past. It looks very different, although it also comes from the ML family of languages. So you have a type call effect, and then you define these types here for get, put m, and update, and then you define a handler for state m. Okay, so far we've seen how to write programs with locally immutable state. It doesn't look too different from what we were doing in F. Might be a good idea to revisit the topic in a different language. Perhaps when you go to a different language, you get a rounder picture of what things are actually happening. Vector addition, okay. Fused effects, ML effects. Camel has only the multicolor one. But this one is interesting. By Nick Paladinos. Let's take a look at that. Huh. There's a paper for doing F directly in OCaml. Okay. Oleg Kiselyov again. He seems to be on everything. I mean, or all of the things around effects that I've been looking at. And this looks small enough to be consumed in maybe an hour of reading it out loud. So this is trying to embed F into OCaml rather than compiling F to OCaml. So I guess you will have a few data types that would define the things that you want, like non-determinism as an effect. Maybe a type. Right here. And then you would have some sort of runner that evaluates these expressions. Okay, interesting. I think that both this bibliography repository and the original, or let's say the F language paper that Mattia Pretnar has written are very good resources to get started with this. I would like some more time to set up, install F in my computer and see if, for example, any of the Merlin toolchain actually works with it, since it seems to be essentially OCaml. To be able to see the types of things as I write them out, because as we saw before, right? When I get something like the state here, it's not trivial to see. Let me rephrase that. It's not easy to see what is happening. It's very simple because there's only one thing you can do, and it's evaluate an expression and then put the result back in there and continue. But it's if you're not used to it, like I am right now, then it's definitely a little magical. Yes, okay. So I would say that for an exploration of what effects feel like when you're building applications with them, or at least toying around with them, I would have liked them to be, part of the function signature, to be able to know what effects I will need to handle. They seem to let me change the behavior of a program a little too much for my taste, without having to change the program, which might be a good thing. It depends on what you're building and how you like to build your programs. Syntax-wise, I was very comfortable with the way that effects were defined. You define it with a keyword, and then you have the type of the value that it will return. Like in here, you even have a function, so of course you can do many things with this. I would like to start a literary programmer and actually read the paper fully and thoroughly to understand really what are the ups and downs of using something like this. Naturally, I won't get an idea of what it is like to program with effects in the large, or I will get what it's like to program with them in the small, right? With a small program, then what happens? It might be like exceptions, the languages where you can throw them and keep them unchecked, that as your program grows bigger and bigger, you need to start to be more defensive, because you don't really know what's going to blow up when or where, right? But I can't really be I can't really say that for this. And of course, this doesn't mean that this is the way that OCaml multicore will behave, which is also something that I should give a shot sometime, one of these days. I might just schedule another live stream for March to play around with OCaml multicore. Anyways, I'm gonna call it a night. this was very fun, very instructive. I have mixed feelings now about them. I was very interested in them, but hopefully I'll learn more about them in a few days. On Monday the 14th, 13th, I think, 11th actually, Monday the 11th, and maybe we'll come around. Again, if you're interested, if you liked what you saw, if you can go to events, there's gonna be a few more events happening this month. I recently released the schedule for February all the way till the 25th. We're gonna be looking at the actor model in Pony. We're gonna read the paper of Algebraic Effects from Mattia Prednar. We're gonna continue building a design system in ReasonML with Fernando from Klarna, Fernando Villa. And we're gonna be exploring native actors with CAF. CAF is the C++ actor framework. The first paper I found published for native actors in CAF is actually really interesting. And we're going to be doing some machine learning in Reason as well later on this month. And by the end of it, we're going to be exploring modern Smalltalk with Faro. So if you like any of this, subscribe. And this video will be available in YouTube as well tomorrow morning. So go check it out. And if you help me get to 100 subscribers, we'll be able to change the channel URL to actually have reasonable coding in here, which I think will be really nice for all the people that are looking for it as well. Anyways, I'm going to call it a night. Thanks for everything, and as always, stay reasonable. See ya.